So today we should continue and do the next assignments. The next thing that we should do is try to parallelize the programs that are multiplying the tensors, vectors, and matrices. And first we will try to parallelize the program that multiplies a matrix and a vector. Then we will work with two matrices and we will discuss on how to decompose this data and in total how to make this work. Then after that we should work with, if you remember, collective communications, scatter V and getter. Getter V, those are different than standard scatter and getter, in a sense that they can be provided with additional arguments to decompose the data in such a way that the data is not totally equally distributed among the processes. So we will work on that, and we will also work with non-blocking communication functions, which are a little bit more difficult to work with than standard blocking communication functions. Not too much, but it can be a little bit challenging. Okay, so I'll start sharing my screen. Sorry, not this one. Okay, and I already opened an Anaconda prompt. I will activate HPC environment, and then I'll start writing my code. I'll save it on desktop, so this is where I will change the directory to. So the programs won't be large, so I will be typing in Notepad. You can use whichever editor you want. The first thing is to multiply a matrix and a vector. And for this, what we have is we have some matrix of numbers, and then we have a vector. Okay. I'm not sure how much you're familiar with this, but we have a matrix of value, and we have values within rows. And then the number of elements within this row has to be equal the number of elements within this vector in order to multiply the matrix and vector. So let's do a simple example. I don't know, something like this. Let this be our matrix, and our vector, I don't know, so what we are doing here is we are having this matrix which has two rows and it has three columns. Okay, so it's 2 times 2 by 3 matrix, and here we have vector which has three rows, and in each row only one value. So what we will get, our output, will be a new matrix which has dimensions 2 times 1, or in this case actually it will be a vector. The first element we will acquire by multiplying the first row of matrix times these values and then adding those together. So it will be 1 times 10 plus 2 times 20 plus 3 times 30. Okay? And the next element will be acquired by multiplying the second row 4, 5, 6 times 10, 20, and 30, and then adding all these up. So 4 times 10 plus 5 times 20 plus 6 times 30. And this will be our result. In Python, there is already a function that does this. So it's numpy function, or let's put NPy for just to make it shorter. And then we call the function dot. And we just specify the matrix and vector. And it will provide us with results. So that's kind of easy. But we should know how it works in the background. So it is row times a vector, and then adding all of the numbers, all of the multiplications. There is let's say 2 ways to parallelize this. In all of the cases, I think it is a good idea to have full vector. Actually, no, sorry. Let's think about the first case. So how we can decompose this data? We have a number of rows here. First, second, third, and so on. Let's say this is an n times m matrix, and this vector is n times 1. So our result will be n times 1. So a new vector of n values. Each of n values is acquired by multiplying the appropriate row with the column, with the vector, and then adding all of the numbers up. So the first element is acquired by multiplying the first row with a vector, and then adding the values. The second is acquired by multiplying the second row with the vector, and then adding the values, and so on. One way to parallelize this is to have processes, sorry, let's change the color, work with rows. For example, process 0 can work with, I don't know, n divided by np rows. First, n divided by np rows, where this np is actually the number of processes. And then each process can work with a similar amount of rows, and they will each have a portion of a result. Okay, so the process 0 has several rows, the process 1 has the next several rows, the process 2 the next several, and so on until the end, and depending on how many processes there are. So the first process will have this portion of result. The next process we have the same portion but shifted, and so on. And then we can merge the results together. So this is one way of doing it, and we will implement this. But I will mention other ways how we could do it. What I showed here is called row-wise decomposition. We can also use column-wise decomposition, where we will divide this matrix along the columns in some way. So here we have n columns, and each of the processes will work roughly with matrices of size n times m divided by the number of processes. Okay, so this is a first portion for process number P0. Then the next portion is for process P1, and the next for P2, and so on until the P and P minus 1. So the last process, I'll write it here, is process with an index of np minus 1. Okay, so if we decompose the matrix like this, our result on each of the processes will be actually a partial result from multiplying this portion of a column, of a row, sorry, with a full vector, and then for the next process, this portion of a row with a full vector. If you remember, to acquire the result, we actually have to sum all of these multiplications, okay? So each of the processes will have one portion, and then we should reduce these values. Each of the processes in this case will have the result of size n times 1, which is okay. Our total result should be a vector of n times 1 values, but each of the processes will only have part of a sum in its vector. So the process 0, this is kind of a little bit more complicated, will have n times 1 vector, which is a result of multiplying these values, okay, with this vector, okay. That's process 0. Process 1 will have a similar thing, just it will be a result of multiplying these values, okay, with this. So for process 0, it was these values, and so on, with the full vector. And final result we will acquire if we add all of these up, okay? So this is a simple reduction operator. We saw that. We can use MPI reduce. So this is a second way. And third way to, okay, I will go back, sorry. Okay. Third way is actually to combine these two ways. I'll try to sketch it here. So we have a matrix and we have a vector. We could do something like this, okay? For example, let us have 4 processes, and we could divide our matrix like this. So the first type of decomposition of this matrix that I showed is a row-wise decomposition, decomposing the matrix by its rows, and let each process have their own rows. The second is column-wise decomposition, where we decompose the matrix by columns. And the third one is called checkboard decomposition, where we divide matrix both at rows and columns for each processes. And this is just a combination of the previous two, but it's, I think, the most difficult one to implement. The easiest one to implement is the first one, and in most cases it is enough. Type of decomposition that you should choose really depends on the size of your matrix. If your matrix is squared matrix, the most efficient way to decompose it is actually this third, the checkboard, the decomposition. But column-wise and row-wise decomposition are equally efficient here. Of course, it can also depend on how sparse the data is your matrix. By sparse matrix, I mean matrices with a lot of zeros. So it can kind of depend on that. Not too much though. When you have a lot of rows, it is better to use row-wise decomposition. And when you have a lot of columns, so if the number of if n is much larger than n, then it is maybe smarter to use column-wise decomposition. But okay, we will just go with row-wise decomposition for now. So once again, row-wise decomposition, each of the processes have their own portion of matrix. First process has matrix of size n divided by np times m. Okay, so m is the number of values here. Okay, n is the number of rows. If we divide that by the number of processes, we will acquire how large the matrix is for each process. What can happen here is that this n is not divisible by np, but that's okay. In Python, I think the smartest idea is actually to use a function that is called array split, and we will work with it. So let's start writing code. Okay. I will save it on desktop, and then I will explain. So this is vector matrix vector multiplication. Okay. Well, okay, we know we will be working with MPI, so we can import it. That's our first line. Then let's start from main function. Okay, we will definitely have our communicator. We will use the default one. So MPI conworld, which is the default communicator that contains all of the processes. We will definitely use a rank of a process. Sorry, that's acquired from communicator. So within this communicator, each of our processes have unique identifier. Process 0 will have 0, process 1 will have 1, and so on. Okay. And let's define here the size of our matrix. So we said n times m matrix, n times n. I don't know, let's say 4 and 8. So these are the dimensions of our matrix, and we will fill this matrix with random values between, let's say, I don't know, 0 and 10 or 0 and 100 or whatever. The data will be at the process 0, okay? So that's how it's usually done. Usually the process 0 has the data, in this case matrix and a vector, and it will decompose the matrix and send portions of matrix to other processes. Okay, so the others have nothing. No. Matrix is none, vector is none. The zeroth process will have a matrix, and we will generate it using a, we'll definitely need NumPy. Okay, so imported NumPy. Our values, let's say they will be between 0 and 10, and this size and shape of this matrix will be n times n. So when you write the dimension like this in a tuple, this is the number of rows, and this is the number of columns. Okay? In a similar way, we will create a vector of random values between 0 and 10, but it will only have a size of m, right? Okay. And here we will write our function that will multiply these two together in a parallel way and then print the result on screen. Let's see if this works. Let's print just the matrix and vector. So it should be done for all processes, but not for zero process. Print values. Okay. Our starting point is main function. Okay. Let's try this. It's npi exit minus np. Let's say we have 4 processes, or maybe just 2 because we haven't done anything in parallel. Okay. Oh, I'm missing this. So, of course, process number 1 printed none, because that's what it has. And process 0 printed the values, so these are the random values. Each time we run the program, it will give us different values here, as you can see. But what we can see here, we see here that we have 4 rows, each of the rows having 8 values, and of course we have a vector of 8 values. So how we will acquire the result? We will multiply this row with these values and then add the values up, and we'll get the first number. Then we will multiply these two and we'll get the next number, then these two, and finally we multiply the last row with the vector and we acquire the result. Maybe we can try also this. So this is not parallel, not yet. And maybe we should print this only if we are zeroth process, if everything works. So the result is we can acquire it using np dot dot, so that's a function dot product of our matrix and our vector. And let's just print it on the screen just to check if everything works. Okay. So maybe let's try a smaller matrix. It's too large for me to multiply all of these values. Let's say 4 times, let's say 4 times 4. That's okay. Just for now, we'll change it. Okay, so 4 times 2 plus 6 times 2 plus 5 times 7 plus 2 times 7 should be 69. Then we have a second row where we have 8 times 2 plus 6 times 2 plus 7 times 7 plus 9 times 7, and that should add up to 140. I trust the function, so I don't think we need to check it on the calculator, but if you want, you can. Then the next number is acquired by multiplying 3 times 2 plus 4 times 2 plus 2 times 7 plus 4 times 7, and then we acquire 56. And the last one is 3 times 2 plus 6 times 2 plus 2 times 7 plus 9 times 7, and that should add up to 95. So this is our result. Okay, let's enlarge this a little bit. Okay, and here matrix vector mol. So this is a name of a function that we will be writing in a few seconds. And within this function, we will multiply the matrix and vector, but in parallel. So we will decompose it using a row-wise decomposition, and then it will give us the result. It will print this result, but only if we are zero process. Maybe like this. That's okay. And we gave this function, of course, the matrix and the vector, and we also gave it this communicator because we will be using inside this function the ranks and the size of the number of processes. So it is a good idea to give this to a function. Maybe we can do this too. I think then we will not be using communicator. So this size is, or NP, the number of processes. I will not name it NP because we will confuse it then with this NumPy. I will write size. And now we can define our function like this. Okay, so we should divide our matrix. And then once we divide our matrix, we will have local matrices, okay? Once we have local matrices, we can use np dot local matrix times a vector. And this will be a partial result, okay? So what's this? This is actually a partial result. So this is a local matrix, this here, this portion, for zeroth process. Local matrix for process 1 is this, the next portion. I should write it. Okay. And so on, depending on how many processes we have. Everyone should have full vector, so that's okay. but this we should divide, sorry. Okay, and for this division, there is actually a built-in function that we can use to make our jobs easier. Let's try that. Your zeroth process, we can use this array split, and let's see what it does. And I will comment this line. Result will be 0 for now, just for our program to execute. It's not, of course, the correct result, but I just want to test this, the array split function. Okay, it seems to be working. Our matrix is of size 4 times 8, okay, and we have our array split function is dividing our matrix into components, into parts, almost equal parts, along the axis 0. So this is the 0th axis, the number of rows along the rows. Is the 0th axis, and our columns are the axis 1. Okay. So axis 0 is like this. It seems to be working, but let's try something that is not divisible, just to check what happens. Here, each of the processes acquired 2 rows, okay? First or 0th process acquired first 2 rows, and the second process or first one, so P0 and P1, acquired the next two rows. Actually, it didn't acquire because we didn't send the data, but we divided the data into 2 almost equal parts. Let's try with like this. Okay, so like this. This is one part of matrix. It has three rows. And we have another part of matrix which has 2 rows. So this kind of works for us. Our total matrix has 5 rows, each of the rows having 8 values. But we are not actually decomposing the number of values within a row. We are decomposing the number of rows itself. So the end value, we're looking at that. And this works. We have here from one matrix, we splitted this matrix into 2 matrices. 0th one having these 3 rows, and the next one having these 2. That's okay. That's perfect for us. What we should do now is actually we could scatter this. We can use scatter function to say, okay, this belongs to process 0, and this belongs to process 1. Okay. If we are having only 2 processes, of course, we can try with more, let's say 3. If we are having 3, first 2 rows would go to 0th process, then these 2 go to the next one, and for a final one, we have only one row. Okay, so this works too. Of course, we could use something like this, where first process has first 2 rows, and then all the others only have 1 row left. Or we can do something like this, where each of the processes only have one row, because we have 5 rows and 5 5 processes. Okay, so the next thing that we should do is we should scatter. Let's put this like in a temporary variable. I'll call it temp. So this temp is actually contains many matrices. Zeroth matrix should go to process 0, first matrix to process 1, second matrix to process 2, and so on. Okay. I think we actually need this communicator too, because we have to write communication functions. So let this also be an argument. And if you remember the scatter function, we should scatter this temporary variable from the process 0, so that's the root, to everybody else. We will save this in a variable called local matrix. So here, no local matrix, we don't have that here. Okay. And it's not for everybody, but if we are 0 process, we have this, and we are scattering all of the values to everybody else. Okay, and let's print this. Let's see if this is okay. It should be okay. Let's just try it. Let's stick with 2 processes. Oh, all right. Okay, seems okay. Process 0 has these values, or this part of matrix, and process 1 has this part of matrix. So 3 rows for process 0, 2 rows for process 1. Works okay. Everybody should have a full vector, so we can just broadcast it from the process 0. Broadcast. From whom? From process 0. Okay. Let's print just in case to check if everything is okay. So local matrix and a vector. Okay, seems okay. Both of them have full vector with same values, which is exactly what we want. And what we can do now is we can multiply these 2 values together. So this is one portion of matrix, and everyone is doing the same thing, multiplying the local matrix with a vector. So this will be one line that we would have written if we only wanted to multiply a matrix and a vector in a sequential way, in a standard way. But if we want to parallelize this, we are first dividing the data among the processes, then multiplying, and then what we should do, we should merge the result. Okay? Or partial result. Let's call it local result, or partial, whatever you prefer. And let's print that. Let's see what we have so far. We can do it like this because we'll already, oh no, we are printing everything. Okay, let's print. Okay, so these are partial results. We have 3 values with process 0, and we have 2 values with process 1. If you remember, the results should be 5 times 1, okay? Like this. The result, if we have n times n matrix and n times 1 vector, Then if we multiply these two together, we should acquire a vector of this dimension n times 1, or just simply a vector with n values. Okay, so we have three, or one part of vector with zeroth process, and the next part of vector with first process. What we should do is actually we should gather into a single vector. So we can call getter function. What we are gathering local results from everybody, but final result will be at process 0. So this result will be, and let's print it. It's still not quite okay, but we are close. So it is none for process 1, sorry, and it has these two values, let's say, for these two vectors for process 0. But we should merge y, because we have local result as a single variable here for both of the processes. We are currently working with 2. And one value, when we gather this information, one value is stored like this, or one partial result, and the other is like a next element. And we could merge this by simply using the concatenate function of everything within the result. Okay, so this is a simple, let's say, workaround, but we will only do this if we are zeroth process, because everybody else will have none here. We specified that we only want the final result at process 0. We specified that here. Okay, this should work. Let's try. Okay, it's working. Let's try with more processes. Okay, of course, we're every time we are getting different result because we are using random values here. Okay, so this is our first program for multiplying vector and matrix. Now we should go to the next one to multiply a vector, no, sorry, two matrices together. Okay, let's try to change this one. I will rename it. Let's call it matrix. So what we should change here? When we are multiplying two matrices, it's a bit more complicated, but not a lot. So we have matrix like this. It has, let's say, n times n values within it. And then we have next matrix, which has, let's say, n times, I don't know which letter, L, let's say. The resulting matrix, these two numbers have to be the same in order to multiply these matrices. So the resulting matrix will have n rows with each having L values. Okay? And how do we do this? We multiply in a similar way that we are multiplying matrices and vectors. We are multiplying zeroth row of a first matrix with a zeroth column of a second, and we are adding all of these values. Okay. Then first row or zeroth row with next column, and so on until we multiply all of the values within the second matrix with the first row or zeroth row in this matrix. Then we go to the next one and multiply everything. Okay. And there is already a function that does this. We can use the same one. We can use dot, but there is also a specific version. Dot is more for matrix and vector multiplication. It can be used for two matrices, but matmul is more efficient. So let's try to use that one. So this is one of the things that we are going to change. We will use different function. We will not be using dot. It can work with dot. That's okay. It's perfectly fine. But we're having 3 different dimensions. Let's say 5, 8, and I don't know, 4. So the resulting matrix should be 5 times 4. Okay. This is okay. We are not creating a vector, we are creating a matrix. So this should change. Let values be again from 1 to 10, that's okay. Let this be matrix 1 and this matrix 2. For everybody else, matrix 1 is both of the matrices are none. So we are creating once again matrices only at the process 0. And here we will call it, let's just call it matrix mul. This should be matrix 1, this should be matrix 2. Okay, so this is the, I think our main program is done, but of course we have to write this. Matrix 1, let's say. Probably no, but these name of the arguments of a function don't have to match this. Okay, I call this matrix 1 here and matrix 2, but I could call it different here. It really doesn't matter. I mean, let's say matrix A and matrix B. That's perfectly fine here. Okay. We don't have to check if this number is okay. In general, you should check whether these matrices can be multiplied. And how you're checking that, you're actually checking like a second dimension of a first matrix and a first dimension of a second matrix. These two should be the same. If they're not, then you cannot multiply the matrices. But here we know that they are the same because we specified the dimension n. It is used for both of them, so that's okay. Okay. We can use this, and we can split the matrix A, let's say, in the same way that we split it before when we worked with with vectors and a matrix. This part should also be okay. And here we can broadcast just the matrix B from zeroth process, because only the zeroth process has all the data. We are sending matrix B to everybody else, and for matrix A we are dividing it in the same way, so it's row-wise decomposition. So for process 0, process 1, process 2, and so on. In the same way that we wrote before when we worked with vectors. Sorry, not that, I want this. Okay, so this part is, I think, okay. Here we have gather, that's okay. But here we cannot concatenate it. Let's try this. just to see what happens. So we haven't even changed the dot. It's okay. Let's try. Let's work with two processes. Okay. And we acquired some part of the result. Of course, this is not the total. Oh, sorry. I'm not calling the right program. Oh, vector is not defined. We haven't changed this. So this should be changed to B. We don't have a vector now. We have a second matrix called B. Okay. This seems almost okay. Not completely though. What we have here is everybody is calculating their partial result, okay, and we have a partial result, that's okay. But once we gather the results, we have three rows, sorry, for process 0, that's okay, and 2 for the second process, the next process. We should stack this vertically together, okay? And what we can call here is a function called vstack. So that's the next difference. Let's try something like this. Okay, now it looks better. So we had, let's just check, we had a matrix 5 times 8 and a matrix 8 times 4, okay? Those are the dimensions. And the dimensions of a resulting matrix should be 5 times 4. And this seems okay. So we have 5 rows with each having four values. So it's really there is not a lot of difference, but here I prefer to use matmul for multiplying two matrices. Of course, it will work in both cases. It will work with dot, so we do not have to change that, but that's okay. What we could do to make this more efficient, we could decompose. We only decomposed here one matrix A. We could decompose 2, or we could decompose in a different way, but this works. Of course, this program will be kind of slower than a sequential version because these matrices are relatively small. It is really small value for a computer. But maybe if we put something like this, our computers will break. I'm just kidding. This is a lot, I think. It's really a lot. Let's try. Hopefully my computer won't die. You see, it takes time to multiply the matrices this large. There are a lot of values here. And we are multiplying, summing a lot of them. Okay, let that work in the background. So this is just maybe a reminder of a functions called scatter and getter. Scatter is, as the name says, it is scattering the values from this variable, and getter is merging all of these values into a single variable, and then we can check this result, how it looks like, and then maybe in this case we stacked it. In the previous case we concatenated the values. So concatenate is just to, let's say, continue. If you're having the values in one variable, the values in second one, then you're just like merging them together in a single value continuously. And this vstack is vertically stacking the values. So we're having one value and then the other one, let's say, below it. These were the results acquired from process 0. These were results acquired from process 1. So there were some values here, here, and so on. And if we stack these two together vertically, we get a matrix like this. If we could concatenate this, it would look something like this, but that's not what we want. Okay, this is still working. I think we can go to our next thing. And I think it's better to try to work with scatter-v and getter-v now. And I think I have already written a program for this, but I don't know, I can write a new one. So what is the deal here? Scatter and getter, which we saw here, are used to distribute the data equally, all together the data equally from all of the processes. Luckily, we have an array split here, and we could use this simple scatter. For example, in C, you wouldn't have something like this, and you would actually use scatter-v even for this kind of problems. But scatter-v is usually used when you do not have equal portions of data among the processes. So you might have 3 values that you should send to process 0 or process 1, and maybe you have 10 values that you should send to process the next process, the process 2 or 3 or whichever one. So the data is not equally distributed along among the processes. This is for scatter. Of course, the reverse thing works too. So if you want to gather the data, you might not want to gather the data in an equal manner. So you might, in this case, you are using this single variable. You're gathering from everyone. But you might want to acquire maybe 3 portions of data from process 0 and maybe just 1 from process 1 and so on. So if you are gathering different amounts of information from different processes, then you should not use gather, you should use getter-v. In the same manner, if you are scattering different amounts of data among the processes from some root process, which is usually process 0, you should use scatter-v. And let's just write some demonstration for this. So it won't be a serious program, but I'll try to write something in order to, I don't know how to call it, let's say variables get. Whatever. So that's the demonstration on how this function works, We'll import MPI. Actually, we can copy some. Let's not write everything from the beginning. Okay. Maybe we'll just have one function. Oh, I forgot to do that. I don't know, let's just use a simple array to demonstrate this, and the array will have the amount of data that is not divisible by the number of processes. Let's say we have array of 27 values, and we are having four 4 processes or something like that. So we cannot totally equally divide the data among the processes. Let's copy this, we will definitely need that. Okay, so we have our default communicator, we have the rank of our process, we have the total amount of our processes, the process size, and if we are the 0th process, we should create the data or read the data. In this case, we'll create it. I don't know, let's say we have numbers between 0 and let's arrange first 59 values, something like that. Let them be integers. Okay, so we are creating an array here. We are arranging the values. And what we should do when working with scalar v, we have as arguments the following. Com dot, sorry, I'm missing p. I'm not sure if this should be whatever. If you're having something, then the returning variable can be written here. What is received? And I didn't spell this correctly. It's okay now. Okay, but we can also specify it here. So let's put it here. Inside of these squared brackets, when we have scatter v, we should have 3 amounts of data. One is the actual data that we are scattering. The next thing is an array of size. Let's write here and size, which contains the amounts of data that we want to distribute to each of the processes. It is usually called counts, so because it is counting for how many portions of data we have to send to each of the processes. And final argument, actually we have 2 more, sorry. The next argument is, so this is the number of data, and then we have something that is called the displacements, usually called displacements, you can name it whatever you want, and that is also an array of size and size. So these 2 arrays have the same size. They have for each of the processes, the array counts has the amounts of data. So its first value or count of 0. Let's write it here. Let n size be the number of processes, and we have counts, an array, which says something like this. If we have, let's say, I don't know, 3 processes, count could say something, 5 portions of data should go to process 0, 6 should go to process 1, and maybe 5 again to the next process. So that is counts, the amount of data that goes to each of the processes. The displacements are starting from where the data should go to that process. So usually for process 0, I don't know why I have made it this large. So this is counts, the amounts of data that are going to each of the processes. The displacements, I'll write it like this, shorter, is, let's say, an index from which the data should start going to that process. It's usually like this. Usually for process 0, the data goes from the index 0. Then for the next process, it's usually this where the previous started, plus how many previous have been worked with. So the previous process is this one, process 0. This is the data for process 0. And we are currently working on process 1. So for process 1, we should start from index 5, okay? And then for the next one, what we are doing the same thing. We are saying where we ended with the previous one, plus how many previous one had. So in this case, it's 11, okay? Let's do it once again. Maybe this again. So for process 0, we are starting from an index 0. For process 1, we are saying where the previous process started, plus how many previous process how many data previous process processed. That's the in this case 0 plus 5, it's 5. Okay. And for the final one, we have where the previous process started, plus how many data it worked with. It started with an index of 5, and it processed total 6 amounts of data. So it should, so we should continue from process the data on this index, on index 11, and work everything, the next 5, process the next 5 portions of data. I'm saying portions of data because it doesn't have to be an array, it can be something else. In our case, it will be an array. So we are having this data like an array. We should, right, that's okay. We should put values in here, in variables counts and displacements. And I missed a final argument. This is just the data type. So the data type here is we are working with whole values. So it is an integer. Okay. Let's fill in the counts and the displacements. And these counts and displacements should be only filled within the zeroth process. All of this. Data, counts, displacements are usually contained within the zeroth process, and everybody else just don't have that. They will receive their portion of data inside of this variable, inside of the variable received. So everybody else has zero data, or none of data. Having what? They are having, we should create counts. And for here, I mean, we have to kind of invent a formula. So what we will do is we will count how many data we have, and we will divide it by but also this should be an array. So one way, I don't know if I have showed you, let's try something like this. This portion of code, well, it will do the next thing. It will create, it will first go within this loop. So for I in range and size, it will create zeros, okay? So we here, I mean, I'm just showing you how this works because I'm not sure if we had something like this before. So it will create an n size amount of zeros, okay? N size zeros. What we want here is we want actually something like this. We want the number of data divided by the number of processes. But these two numbers are not divisible, might not be divisible by, it really depends on how many processes user runs. So here we could, if this is divisible, then everything is okay. But if it's not, then we should use a whole division. This is a whole division for starters. If it's not, we could add one for some of the processes. What I mean by this, for example, here we had 16 portions of data, but we had 3 processes. 16 is not really divisible by 3. We have, if we divide it by 3, we will get 5, and we will have a remainder of 1. So this one should go to somebody of these 3. Okay, everyone will work with 5, but someone has to do 6 portions of data in order for the 16 pieces of data to be completed, because we only had 3 processes. For now, what we wrote here is, for now, if we don't have this +1, we only have this 5. So maybe somewhere we should add 1. Where? I mean, there are several ways to do this, but we could add 0 or 1. 1 if the process is, let's say, less than this remainder. We have a remainder of 1. And how do we write remainder in Python? It is a lot of things happening in a single line, but okay. We are adding 1, or otherwise we are adding 0. So in this case, first of our processes that are less than the remainder that we have, their IDs are less. This I here stands for ID of a process. Maybe let's even call it ID of a process. It's clearer. Okay, so if ID of a process is smaller than the remainder, in our case, let's say if we have 60 and a remainder of 1, it will be true for 0th process, and he will work, or it will work, with 6 portions of data, okay? Otherwise, add 0, okay? So everybody is working with 5, but if you have a remainder, first IDP processes will work with 6 portions of data instead of 5. Okay, so the total amount of data divided by the number of processes, and this is a whole division, and we are adding 1 or 0 depending on the ID of a process. I should have written this in a loop, so it's easier for you. So this is one way to write this in a single line, but I will write in multiple because I think it's clearer. I'm just translating this one line thing in more lines. Okay. So the value is the length of data. This could be outside of loop because this doesn't change. So this could be here. Let's try things more efficiently. And then if IDP is smaller than the remainder, let's add 1 to the value. Sorry. Okay. Let's just double check this. Let's print both of this. Maybe I messed something up. I think I haven't, but let's just try it. Okay, and let's comment this. This is called, oh, sorry. Oh, I have double R's here. Okay, seems fine by me. So here we have 59 portions of data, and the zeroth process should work with 30, and the first process should work with 29. Maybe let's try 3. So if we have 3 processes, first 2 will work with 20, and the final one, the final process, will process the 19 pieces of data. That seems okay. If you have 4, we have something like this. If we have 5, we have something like this. If we have 6 processes, we'll have something like this. If we have 7, we have something like this. So this is maybe a more interesting one. The first 3 processes are working with 9 values, and the next processes are working with 8. So we are either working with the total amounts of data divided by a size of process, by the number of processes, or we are adding 1 to this value because this is not fully divisible. For example, here, 59 is not divisible by 7 processes. So everyone is working with 8, except for the first 3 processes will have 1 additional pieces of data. What you could also do is you could just say, okay, this has a remainder, add everything to the last process, for example. But that's kind of not fair, because then the last process has much more data to process than the other ones. This could make sense if you are sure that the last process will get maybe a faster processor. That's okay then. You can control this, kind of. But in a general sense, it is usually a good idea. You shouldn't be dependent on your environment where your program is executing. You should assume that your processes will be of similar strength, okay? Or of similar speed. Well, let's not use the strength. Okay, I don't know which one is easier for you. For me, in the beginning, this was easier, but now sometimes I write things like this, but both are the same. So let's leave the first one. I think it is a little bit clearer. So these are the counts. How many pieces of data should everybody process? How many zeros, how many first, and so on. Okay, well, maybe once again explanation for this. This is if ID of a process is smaller than the remainder, then you should work with one more value. You should process more values. Fine. Okay, let's put counts to none. What we should do next is we should calculate the displacements, and the displacements are kind of easy to write once you have the counts. If you remember, you're calculating the displacements by starting from 0, okay? And then for every next value is actually the summation of these previous two. So the summation of previous value in a displacement array plus the number from an array of counts, okay? Or you could simply just summarize the value in counts all the way until the ith index, or the, let's say, IDP. Okay, this should be our displacements array. Let's check it. Let's print the displacements, and also let's print the counts. I'm not sure if I should comment on this. Maybe. Let's try once again with 7, and of course we get this array. And so what we are doing in a displacements array, we are summing all the values until the IDP. If you remember this, the first value is assumed here, and we are going all the way until the next index. So when you're indexing the variables, you're doing from where you're starting until where you're going here, and by which step is the next variable. Assumed one. It is assumed that you have 1 here and 0 here. Okay, so you can write something like this, and if you write something like this, that means go all the way until this value. We are summing the first 0 parts of the counts, and we will only get 0. Okay, so that's this value. Then we are summing only first value, that's just 1. Then we are summing first 2 values, that is 18. Then we are summing first 3 values, that's 27. Then we are summing first 4 values, that's 35. Then we are summing first 5 values, that's 43. 43. Then we are summing all of these values, first 6 values, we are getting 51, and that's it. We are stopping there because we finished our loop. Okay, so this is the loop, and this is just like a summation part. Okay, so now our scatter wave function is ready. It took a lot of time to prepare it, but that's okay. Let me just think. I think we can try this finally. We could leave those prints too. I think they're okay. Let's print counts. Let's print the displacements, and let's see what happens. Maybe we should also print the process ID. So rank and received. Okay. Oh. Yeah, we haven't defined the received variable for starters. We can just allocate the space for this. Let it be an empty numpy, which has how many data it should have. The amounts of data that are already in counts, but it depends on the rank, right? So because we have, there is one more thing that we should do here, actually. So this counts is only within the zeroed process. For everybody else, it is none, but it has the amounts of data for each of the process to process. So for zeroed process should process the amounts of data that are written on a zeroed place. The first process should process the amounts of data that are written in a first place, and so on. What we should do here is we should broadcast to everybody from the zeroed process the counts. The zeroed process, this is root is equal to 0, we are broadcasting the array counts, and everybody now has it. So now it's better. We could also broadcast the displacements. I think that's okay too. And now we should be ready, because we have allocated the space for the received variables. Without this, it was not allocated, so the program could not write here. It didn't have a memory where to store the data from this scatter. So this is important too, this part. But to write this, we have to know the values within our counts array, and we have them only at the zeroed process. So before we did this, we had to do this. We had to broadcast the values from an array 0. And let's try now. Oh, once again, I think it's just something misspelled or something like that. Let's just check. Yeah, it finished most of the parts, but then, oh, we haven't specified the displacements here. We should. Let's try once again. Okay, now everything works. So these are mostly the zeroed values. But why? Let me check. Maybe let's try with a smaller array and with 2. Okay. We should match the data type here too. That's one thing that I'm missing, that I see. We are working with an integer values, so that's one thing. Here we either have none, or we have the data from the zero process, which I think is okay. Okay. Let's check everything. Let's also check counts and displacements within each process. So everybody should print this counts and displacement just for us to check. if that's okay. And maybe let's print rank 2. Let's try now. Okay, now it seems to be okay. I think the only thing that I was missing is the specification that we're working with integers. Let's then remove this. Try once more. These are for true processes, for 7 processes. Yeah, everything is okay now. So this is how we divided the data. First, 9 pieces of data went to the 0th process. The next 9 data went to the process number 1. The next for process number 2, and then everybody else, I think, acquired 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So the first 3 processes acquired 9 portions of data, and everybody else acquired 8. And these are just the values between 0 and 58 that we specified here. Okay, so this is the scatter V. The getter V is just like the opposite. We could merge this data that we acquired in the variable received and get them back in a single area like this. Let's try that. So what we have here is we have a chunk or a piece is a first argument, and that's actually what we have received here in a getter. So we are doing just the opposite thing. You won't be doing like this in your program probably, but this is just a demonstration of how these functions work. And then the next thing is where we are gathering. Let's gather this in a result, no, not in this data array. Let's write it somewhere else. I have misspelled this first variable. Okay, so that's the first thing, and the next is just counts, displacements. Maybe I should just copy like this, not risk to make any spelling errors. Okay, and we should specify in the end to whom the whole data will be gathered. So this result will contain all of the data, but we have to reserve the memory. So if we have 0th process, we should reserve the data for result. I will do this here. And if we are not, if we are everybody else, we could say result is none. How we are reserving the data, the same as before. We have the amount of that's actually the length of data, but let's write something else. Let's say that this is the sum of all the values in the counts variable. Okay. This should be, I think, okay. So everybody is sending here what they have received. Maybe let's try something to let's change this received. Here they are receiving, and then everybody should merge the data. But let's say we have, I don't know, a square value or something like that. So everybody should raise the values that they have received to the power of 2. Let's say that's okay, and then we will gather all of the information and print what we have gathered on the 0th process. It will be a 0th process, so that's okay. We'll put this gathered information will be within the result. Okay, so we had a single array of data with values between 0 and 58. We divided them almost equally among the processes, and then we gathered the data back together we squared everything. So each portion was squared, and then we gathered everything once again in a single array. So these are the values between 0 and 58, but squared, raised to the power of 2. Okay, so this is just a demonstration of scatter-v and getter-v. They are working in a similar way that the standard scatter and getter are working, but we are having the variable amounts of data that we are sending or receiving. Don't forget to allocate the memory for function. That is a common mistake. So yeah, I think that's it about variable getter and scatter. Okay. Now let's go to the non-blocking functions. And I think in order to save time, I can open the code that I have already written before. Just give me a few moments to find it. I think I can find it somewhere. Okay. Yeah, that's here. I will upload this later. So what we had so far is each MPI call, each MPI send, each MPI receive, scatter, getter, broadcast, and so on. Everything was a blocking call. Once we arrive to that line that has an MPI function, each process that is ran on a computer, I mean by our program, will wait until this communication function completes. So in this example, we have something different. If we have non-blocking function, we will send the data, and then we will continue executing our program. So this is not how it worked before. Before was we are sending the data and then we are waiting. We are waiting for somebody to receive this data. Okay. Also, if we call receive, if we are process receive, okay, we are waiting. Here we are definitely waiting. We are waiting for somebody to send us the data. Okay. With these calls called I send and I receive, the function is almost the same. We are specifying what we are sending. So this is just a piece of data. It doesn't matter. We are sending it from the process I. We are sending it to process I, and the tag is 11. So what we are sending, to whom we are sending, and we specify some tag. It can be even omitted. It's not important. We put 11 arbitrarily, so it's not really there isn't some sense behind this number. Okay, and then we can do something else. Okay, we said, okay, I will be sending some data, but I will not be waiting for them to be sent. And how this is usually done is if you're sending the data, for example, to multiple processes, you will have an array of requests, or name it whatever you want. Then when you send, you append this request to your array of requests. This is a single request, and you do something else here if you want. Then if you want to wait for all the requests to be completed, so for everything that was sent here to actually be sent, okay, so this is just like a preparation. I will send you this data, this will arrive. But then when you call npr request wait for all, then you're waiting for each request that is inside of this array, okay? So we are waiting for every request at line 20, not before. And once the all data is sent, okay, we say all the data has been sent. So this is a new function, wait all. It waits for each request within this array. The next thing, let's go to actually to worker. So this is a process 0. It sent the data to everybody else, and then it waited for this function for all of these send functions to be completed. The worker process created an empty data, and it said, I want to receive the data, but it is not a blocking call. So here we can do something else and then maybe wait for a request to finish. So this is a blocking call. If you say request.wait, then you will wait for this message to be received. Here on the line 43, you're not waiting for the data. You're just specifying, I want to receive the data from process 0 with the tag 11, and I will put it in here once it is received. But you're only waiting for the data once you call this wait call. Okay, once you do that, you multiply the result by 2, and then you send the data back to the 0th process, so it's multiplied by 2, it is two times larger, and you're waiting for your send function to be completed. Okay, so this is what we are doing as a worker. As a master process, as I said, we have already sent the data, and we are here. So now we want to receive all the values from everybody else. We put the results. So these are the results. This is just we prepare the array here. Then we have our received requests. What we are doing, we are preparing our buffer, so the storage for everybody's data. We are calling the receive function, from whom we are receiving. We are expected to receive the data from the process number I, so for first, second, and so on, all the way until the end. And we are putting this request inside a receive request. Here we decided to, for receive request, to have actually a couple of data, two data. One is the actual request, so the actual request for receiving the data, and the next thing is a value that will be received. And then once we have called all of the once we have requested all of the data to be received, we can wait for them in a separate loop. In the meantime, here we can do something else if we want, because these are the non-blocking calls. In this loop, we are going through each of the requests and we are waiting for them one by one. We could wait for all of them, but since we have written the result like this, we will be appending the results from the buffer. So we are going through each of the requests. We are actually acquiring two variables, these two that we have put here. So one is the request and the second is the value. We are waiting for a request, and once the request is completed, we have obtained the value within this buffer variable, and it is appended here. This is from 0 because we know that this is an array of size 1, so we are just putting the divine value, but we could use a full array here if we wanted to, or dictionary or whatever. So yeah, what's important here? It's important here to note that the request has to be waited in a separate loop. Don't put this here. So that's one important part not to do, because if you do something like this, then you're waiting for requests one by one. So this will be the same as a blocking call. If you're sending a receive and then immediately after that you're waiting inside a loop, then this is a blocking call. You're expected to receive the data from the I process, and then you're waiting for it. If you put it like this, then you're waiting for the request to be completed after you have sent all of your received requests for everybody, for each of the processes. So that is important to know. Okay, I think that pretty much sums the worker and masters functions. I'm still not sure what kind of project you will receive. Sorry, my throat hurts a lot. Maybe it will include these non-blocking calls, but we will see. We'll see about it. Are there any questions from your side? I think these two, this class was the most difficult one, because we have matrices, we have the vectors, then we have this scatter v and getter v, which are a bit more complicated, and then we had non-blocking calls. For tomorrow, I think we will just go through everything that we have talked about so far. I mean, a bit shorter, of course, just to summarize everything, and then I will note to you maybe some other ways of parallel programming that haven't been mentioned here. So throughout this course we have been only working with MPI, but that's not the only way to do high performance computing. We will talk about GPUs a little bit tomorrow, and I will show you one of the ways on how to use computing cluster. By that I mean how you can track everybody's jobs. I mean jobs in a sense of they're running processes, they're running simulations. How you can track your own, of course, and how you can specify, for example, how many processors you want to be used by your processes, how many processes actually you want to run with your simulation, and something like that. If there are no questions from your side, I would like to finish for today, and see you tomorrow. Bye. Oh,
thank you. Goodbye.